fulfill the task, then I'll give you the second chance to do the task individually.
Okay.
Like with some manual corrections or whatever you guys want to do. But be aware of that the mark will be deducted because in my rubrics there's an item about automation. Okay, so if you guys are ready, then you can get started.
You just stand on the side.
Oh.
In this case, it will follow the edges. When it sends the IR sensor in the charging station, it will go to the mode 2, where whenever it reaches the ends, it will try to turn a randomized angle, try to cover the whole room.
So we have overshoot.
Yeah, because he sends the charging station.
And when the bus bin is full or it is out of battery, we will press the press sensor. And we'll go to the status 3, where we try to return to the charging station. Should we turn this on? Yes, we turn this on.
That's it.
You have a docking process.
And we have to demonstrate. And we have another thing to demonstrate is the obstacle avoidance in the line following mode.
Yeah,
You
for
can see
example,
we have a lateral lateral ultrasonic sensor, so we use that to avoid the obstacles. We will try to follow the edge instead of just turning away.
But we are asking for an
Yeah.
obstacle in the middle.
This one is just
This one is for the mode 1, where it tracks the edges. When in the mode 2, the line followers, it will just simply turn the angle when it's
Okay, so that just demonstrate to me.
okay. This one first.
Yeah, this one first.
This is the first mode where you trace that edge.
It has some edge cases, but it's okay.
Yeah.
So where did you get the second ultrasonic sensor?
Yeah, we find the bus bin.
Take
Yeah.
It
Yeah, it
tracks
checks
me.
A bit unfair for the other groups because they all get one, but you have a new mode, so
Yeah.
I'll count it as an improvement.
Yes. So if
But it
goes
does
to-
have a lot of overshoot cases, did you see?
Yes.
Okay, so yeah, already turn it on.
Then you'll start into a mode to where you rotate and go randomly. Then if there's an obstacle, you will turn by random angle as well.
No, let it dork me, right? You are turning on the IR sensor, so it should dork.
No.
When you turn on the IR sensor means that once it sends the
No, this is the mode 2, where if you press the pressure sensor, then you will feel that that flex flow, right?
So the switch between mode 1 and mode 2
Is
depends on
by
IR
this
sensor.
one. Then the mode 3 and mode 2 depends whether or not
we can show it in this.
Okay, just show me the central obstacle. Yeah, that one. So when it sends, it will
turn by random.
you have some overshoot cases. Quite a lot, I would say.
It's because it has the
Oh, I get it. Oh. So your obstacle avoidance is done by rotate back or random angle?
Random angle.
Random angle.
Yeah, just random angle.
Because it senses the obstacles.
Good.
It's an addition of the sensor.
When it senses the obstacle, it will just.
Yeah. And the reason why we set up two modes is because in the random work status, it won't fully cover the edge cases. So we first traverse the edge to to fully cover the room better.
Yeah, because it's hard to clean at the edge. So we firstly, in mode 1, we try to clean that
Yes.
first. And then we switch to mode 2.
Okay, can I see the IR array? You don't really have any resistors to limit the current.
Yeah, because we think that we test the voltage for it to work with a certain distance. Then originally we have one, but eventually, yeah, even
Have a resistor here.
Oh.
Yeah, it's blocked.
yeah, but it's in the back.
Oh, so you okay, get it.
But we changed into a smaller one. Yes.
Actually the major cores didn't need this lateral sensor. This lateral sensor is only for tracing the edges when it encounters obstacle, and it have to maintain a distance between this side and the obstacle. So
Yeah,
it's
get
use
it.
this one. So actually the main function doesn't need this one.
Yeah, I get it. I'll count it as an improvement. Although you get one new component, but you make some new functions, which is nice, which is something we encourage you to do. So I will count it as an improvement. Very nice. Can I see the soldering? The soldering of the. Is it possible to
Because
dismantle this?
it's under beneath.
So already glued?
Yeah,
Yes.
yeah, I would agree with that.
See something? Okay. Looks good. As long as you can glue this, means that
Maybe we can.
your
Can
soldering
we
is.
basically simply?
Yeah, you can
show
see this
that?
is the status transition. The status-
Okay, okay. Explain this to me. I'm
Okay.
interested in this one. Okay. Tell me how did you do this?
Yes. So we have 4 status. The status 0 is just if it is idle and it won't work. So at the same time it is status 0. And when we press the start button, it goes to status 1, where we have different controllers for the movement. In this case, controller is the edge follower.
Okay.
The edge follower we have a logic for it, and we'll explain later. And so in the status 1, it will go through a cycle of the room, and when it returns to the charging station, which is that is sensing the IR, it will change to the status 2, where it starts to go randomly.
Sorry, what's the transition from start 1 to start 2?
It's like it goes around the
Goes
edge
around
and sends the charging station one second.
return to this.
Okay.
Like
So it means
this.
that the transition between stages are all triggered by the IR sensor, right?
It's not all the case.
So from 1 to 2, from
Yes.
2 to 3, they are.
From 2 to 3 is press the
Pressure sensor.
Also, status 3 will be the dust bag
The-
full cases.
Yeah,
Yes.
then it will go
Ah.
around the edge again, then
And
return
turn
back
back
to
the
the
again.
Yeah. then
Yeah,
return
so
back
actually
to
the
charging
status,
station.
the controller for status 3 is the same as the status 1, where it follows the edges and avoid obstacles when it sends one. So for the edge follower, it is we are only using the grid style sensor, the line follower for at the front of the bandboard to control it follows the edges. So the logic is demonstrated in this graph. When it sends when it's off.
Yeah. I get
Yeah.
this mechanism from your graph.
Yes.
Okay.
So for the obstacle avoidance, it's like much more complex. So first, it will sense the object using the front sensor. When it senses the obstacle, it will turn a large angle, and then it will try to maintain the distance between the side of the robot and obstacle using the lateral sensor. It will try to maintain the distance is in a range. When it's too large, it will try to steer inward, and if it's too close, it will try to steer outward. And if otherwise, it will just go forward. And to exit the obstacle avoidance mode, it would the condition is to sense some black part for the line follower. When it senses the black part, it will exit obstacle avoidance mode and goes back to this logic. Yeah, and so for the random worker, it's just much simple. Just when it sends the edges or one obstacle, it will try to turn a randomized angle. Why we made it randomized is because we want to avoid that cycle case possible when it's reached the edge of the room.
Or between the background and the
Yes,
obstacle.
yes.
Yeah, because some of the function originally, if you don't do randomize, it will do like this and this because it's like our algorithm will limit it to the right angle. But if we turn into make a randomized angle, then
Yeah.
whenever it sends this, it will turn randomized.
Yeah, actually,
Yes.
there's a limitation.
What's the range of this randomization?
Because the turning is determined by the time of the rolling of
Time
the
interval, whatever.
Yes,
Yeah, I
the
mean,
modal status.
What is the range, like from 0 degree to 330 degree?
I think it's 270 to like 800, like the time. Is it?
I think it's like 180 and between 180 and 270.
It's because we use.
So
We use millisecond for
Yeah,
to
yeah,
determine
yeah.
time.
Yeah, so actually it's not that correct, not that accurate for this.
Yeah. We just test it and we
because
set
in
the
our case,
parameter.
Okay, so
Yeah,
you
so
are
just
Mhm.
it's
more or less like an
Yeah.
angle, but since the steering depends on the motors,
Yes.
but you are only setting time for the motors, right?
Yes,
Okay.
because we cannot just tell it to change a certain angle.
Yeah, I get it.
Yeah, so this is all
Your understanding is robust. Okay, let's scroll down a little bit to see.
So that is the introduction.
It's the design part.
Okay. I really like your prototype. It looks quite good, but there's one edging cases where you didn't do it well, which is your robot will
Yeah.
potentially
Yes.
overshoot the
Yes.
boundary.
That's one of
That's
our
for the
limitations.
status too.
Yes, because
So maybe the randomized angle, this can be improved later.
Yeah, so it will overshoot, and your line follower will detect nothing, so it will just presume your robot is in, I believe,
yeah, it's still
Yes.
yeah, still in data 2. Yeah, because it just overshoot and then detect nothing, then running around. Yeah, but it's quite good. Like I like your status transition. You're really discussing different
And
status.
actually, there's another limitations where our obstacle is only limited to the obstacle with a curved edge. If we use a plane that is not placed perpendicular in front of the sensor, it will sense a error value, a wrong value.
Specifically at the
So,
corner.
Yeah, specifically like this, it will sense. Because I think it's because the
Can I see
sound
it?
wave.
Can I see it?
But the computer was.
Just maybe you can.
那个数据线，那个线，那个线
It's
对的，真的。
And I think it's impossible to fix this because it's the intrinsic problem for the sensor.
Yeah, I just want to see it since you mentioned this.
right now it's in the live hour mode. Yeah, and
Yeah.
this part will be no.
Because this sensor's reading is not correct. Yeah, like that. The sensor.
Oh, it would try to track the edges, the square edges.
Yeah, but actually the okay. Actually, we can demonstrate it by connecting into a serial monitor to see the actual readings. Can restart it.
It's 9:17 already. Just let me see it. Oh, we are coding using
Yes.
VS Code.
Yeah, because we can have the intelligence
Yeah,
function.
I get it. That's quite good.
Yeah, you can see the lateral distance from
Okay.
here, and like that. That it's correct. But if we turn it, you can see
Yeah, so it
reading
bounces
is not-
away. Okay,
Yeah.
I get it. Okay, that's quite good. You really know your sensor, you have a good logic, and even though your robot have one pitfall which is overshoot, but generally I really like a demonstration, so
Okay, thank you.
why not go listen to your presentation. 15 minutes timer right here. When the time is up, you are going to hear alarm. So if you haven't really finished your presentation, please wrap it up in 1 minute. Otherwise, I'll just interrupt your presentation and we'll call it a day. The rest of the content I won't pay attention. Okay?
We will get penalty if we exceed a little time, like up.
1 minute.
Yeah.
No.
Oh.
1 minute is okay. Like you just quickly wrap it up.
Just press and
Thank you, sir. Okay, if you guys are ready, then I'll get started.
Hello, we are Group 1, and here is a robotic vacuum cleaner demonstration. And first is the introduction. Our design requirements mainly contain 3 parts. The first part is coverage, and the second part is auto homing, and the third part is the alarm. And I'll hand it to my teammate. So here is our robot design. This is our modeling for our design. Its dimension is right here, 8 centimeter height and 35 centimeter radius, and it comprises of four functionalities: power, control, navigation, cleaning, monitoring, and user interaction based on our proposed IoT app. So this is our overall functional diagram. It comprises of 4 phases, and our software system really mainly realizes 3 functions: the control system, the moving system, and the design algorithm. The moving system is basically the same with our demonstration, so we will focus on the first and third one. So here's our control system. We get data from 5 different sensors. The image from the camera will be processed by the neural network to identify some obstacles, like the cable on the ground or clothes on the ground, which are hard to be detected by other kind of sensors. And the radar sensor will get real-time position of the robot, pressure sensor to avoid incidents, grayscale sensor to avoid any drop, and dustbin sensor will monitor the real-time dust level in the dustbin. And here's our basic ideas for our algorithms. We want our robot to be able to memorize the dust distribution. So we've implemented 2 maps in the robot. The first is the memory map. While all our algorithms is based on the data in this map, it records the distribution of the dust. And second map is created. The robot will create a learning map based on the increase of the dustbin pressure. So we will divide our room into different cells, and we want our robot tend to visit nearby cells with high dust levels. So we assume that each cell will provide a force, and the possibility of the robot turning to different directions will calculated by the force. And we want our robot tend not to visit cells behind the obstacle, but the dust near obstacles is hard to be cleaned. So that means we want our cell to not to go straight towards the obstacle, but to go around the obstacle. So we have made some temporary modification to the memory map so that it can realize it. And we want our robot tend to enter another room if the current room is almost clean and the other room is large and uncleaned. So this is a possibility of the robot going to another room when it encounters the door. So here's a simulation of our proposed algorithm. The dust distribution is generated by wave collapse algorithm, and we will initially assume that the dust distribution is uniform. So it goes like this. And after one time of learning, we will put the learning map into the memory map so that it will allow a more precise control for our robot's behavior. As you can see, this one is much cleaner compared to this one. And this is our outcome for learning 3 times of the dust distribution. And it provides a strong benefit to our algorithm, which will be discussed later in the evaluation part. So here is the whole functionality flow chart of our design algorithm. It has 5 different phases. The initialized phase, the user will input a floor plan. So we have a standard map algorithm to divide it into different rooms, And in each room, we will implement its prepare phase and the cleaning phase, which has been discussed previously. And we want there is a report phase where our robot will report the status of the robot and the dust distribution to our design app. And we want our robot to have the functionality to report error. So here's the decision when it reports that the robot is getting stuck or is unable to exit a certain area. So here's the calculation.
Start with our calculation. We need to look at the requirement. The 1,000 square feet information is very crucial for our calculation and power consumption. And our calculation will be based on this logical flow. We decided to let the diameter of the robot to be 0.35 to 0.3 meters and the height to be 0.08 meters. And the designated speed is 0.2 meters per second, and the robot's wheel status is 0.035 meters. And the estimation of the robot mass will be the battery mass plus motor mass.
Wait, can I see the robot wheel radius?
Yes.
Oh, that's wheel. Okay.
Yeah, wheel radius, not the robot radius. And the mass, the estimation mass will be the battery mass plus the motor mass, and the shear mass will be calculated from the polypropylene using the dimension of a robot. And summing up all the components mass, the final estimation will be 2.5 kg. Thus, our motor needs to have enough torque to overcome the friction on the ground. And the required force to overcome resistance take into account of the common materials rolling resistance coefficient. We pick the largest coefficient of 0.233 times weight. We found the force required. And the total torque required is found by the force times radius, which is around 0.02 Newton times meter. And the choice of our motor stator sheet provides this torque and a low speed on the 6-volt supply, which since one single motor's torque is around 0.098 Newton times meter, which is greater than required 0.02, and the maximum speed we calculated is 0.641 meters per second, which is also greater than our designated speed, which is 0.2 meters per second. So the motor is justified, and the weight of the motor is also smaller than our estimation. After justifying the motor, the error clean per minute can be calculated by multiplying the length of the roller brush and the operating speed, which is 2.4 square meters per minute. And for a 1,000 square feet room, the minimum time required is 41.67 minutes. And based on our algorithm, the estimated time is around 1.72 hours, and let's assume that it to be a maximum of 2 hours when it encounters the extremely dirty condition. The time it will be also greater than the minimum time, so time is justified. Knowing all the components working power except the battery, the total power consumption can be calculated, and we take into account of 30% of losses, and it will be 20 watts. Therefore, a battery of no less than 4.76 ampere-hour is required based on calculation for 2 hours of working time based on 20 watts. Ultimately, our calculation of the 12-volt 7 ampere-hour lithium rechargeable battery, which satisfies the requirement mentioned previously. Its weight and size also fit for our robot. So I'll hand over my time to my teammates for a bit of materials.
So I'll be discussing component choice real quick with Jerry. And so the first one is power system. And based on previous calculation, we choose the battery with specification of 12 volt and 7 ampere each. So the reason we choose the lithium iron phosphate is because it has high safety and also high charge and discharge efficiency. So next one is control and navigation system. One of the advantages of STM32 is that it has a flexible memory options ranging from 512 KB to 2 MB. So during the demonstration, we have found out that the flash memory of MBOL is really small. It cannot play much longer songs because due to the limit of 32 KB. So I want to emphasize the hinge lever micro switch. So in design, it serves as a collision sensor and output analog signal. So I will hand it over to Julian.
In terms of cleaning system, we have four motors, 2 of them to power the robot and one of them to power the cleaning brush and one for the mini roller brush. Here are the components in the robot. And here is the monitoring part and the miscellaneous. I want to especially say that we are adapting to a public mode to reduce our development and manufacturing costs.
And the last part is our evaluation onto our project, onto our design. The first is our key advantages. We can do smart mapping and editing used to make the user customizable to edit the rooms. And second is our high efficiency compared with the traditional random task robots. And the third part is the full automation of our robots. And there is two limitations of a robot. First one is the low precision in obstacle detection because it fails on sub 5 millimeters objects and fails in environment with no luminous. And the second part is the CNN image processing usually costs a high computational power. And here's our reference, and we'll go into the Q&A.
Wow, that's really a mouthful of things even for me. You did really implement a lot of novel functions, including the control mechanism and some cutting edge technologies like object detection and other like I won't say fuzzy control is a cutting edge technology, but yeah, it's really a novel thing for your batch. Like you are only in year one, but it's pretty impressive. So let me just ask something. Maybe I'll ask some of the shallow questions. All right. So first of all, is the rolling coefficient or something, rolling resistance coefficient?
Yes.
Kind of where do you get this?
I get it from actually a kind of paper. Yeah, it's cited below. Yeah, I have the range of from 0.008 to 0.0233.
So it's a website, right? It's not really,
Yeah, it is kind of from a paper from a conference.
Oh,
Yeah.
okay. So maybe next time you don't really put in any link right here, because visually I can't read the link, right? Maybe you need to put in like the correct format, like which conference, like ICLR or AAA, something like that. You just, yeah, put in the conference name or whatever. And another thing is the time calculation. Yeah, so I believe the logic of time calculation is you have the total room area and you have area clean per minute. So do the division, that will be the time required, right, to do the cleaning. But I believe in your control mechanism, it will make some randomness.
Yeah, this is the minimum time required to clean the room. And based on algorithm, it takes like 1.74 hours, which will estimate to 2 hours.
Oh,
Yeah.
so where did you get this 2 hours?
It's right here. For our simulations, we have set the average meeting time of each cell, and based on that we can calculate the time. Like for the average, each cell is visited for 3.08 times. We assume that the dust distribution is from 1 to 3, which means it will be cleaned for 1 time to 3 times, and with a 90% of dust being.
Yeah, where do you get this 11.8 times for random test robot? You do the benchmark or?
Just from the simulation we made from this simulation part. Yeah.
Oh, that's impressive. So the upper one is a random or is yours? Which one is yours?
These are all ours, but we assume that the dust distribution is uniform in the room in the robot memory. But this one is we have learned some about the dust distribution from here, so we've implemented it here so that will allow a more precise control.
Why your robot can learn this distribution?
Yeah, because
how is it learned?
it's right here.
It detests the dust level of each cell.
Yeah, it is because we can like in this learning map we can take the increase of the pressure sensor in our dustbin and
Yeah, but I saw it's a uniform distribution.
yes. Oh, we learned from this real distribution.
At first, it's
Yeah.
Actually,
At first,
the one I
it's
said
rendered.
to
Yeah.
uniform-
This is the real
uniform
distribution in our room, and this is the map in our robot memory.
Oh, so it's like you have a default distribution.
Yes.
And
Yes.
but you initialize the memory uniformly.
Yes.
So after traverse all of the area, it will know what the dust distribution is going to be like.
Yes.
Right?
Yes.
And it will modify its memory map
each time it cleans the room, and so it will be more and more precise. Like right here.
Wow,
This is
really
the
impressive.
this is the memory after 3 times of cleaning.
But why? So actually, this kind of learning is more about recording, right?
Yes.
Yes.
So your robot will know exactly the location of itself, right? So the robot will know I'm on grid X and Y.
Yes.
Is it?
Yes.
So it's like memorizing, not really learning, right?
Yes.
Learning means that you have some mechanism after feeding some data, your system can perform better next time. But
Yeah.
here you are just memorizing the pattern.
Yes.
But which is already good, which is already marvelous in my eyes, right? So you really want to do something very different. And can I see the flowchart diagram, like
For the algorithm.
yeah, function diagram, like
This one.
yeah. So I need a functional block diagram to show the interaction between every systems.
Oh, the sensors.
You mean this one?
No, I think there was one I
Oh, this is not really a functional. Yeah, so I believe your functional block diagram has some issues. So usually, like this one, right? This one
Yeah.
is more like a logic diagram,
Yes.
right? I will do this when I encounter this, or I will do that. So it's more like a pseudo code or a logic flow.
Yeah.
But functional block diagram refer.
The information, the energy, and the
Yes,
yes,
exactly.
I know that.
So you should have those, right? You have a very nice control mechanism. You have some sensors. You have your chassis. You have your wheels, and you have a battery. Like, what's the interaction between them? So I will not say this is a valid functional block diagram, but I'll say the control mechanism is really marvelous. Like for year 1 students, it's
Yeah.
already very, very marvelous.
I mean, if we put
you
everything,
have a benchmark and
include different sensors and other.
yeah. Just like another question I didn't really see is you claim your robot is better than a random robot.
Yeah.
Where did you get the data for the random robot? You get it from some paper or you do the simulation?
We just do the simulation.
Okay, I see it.
The code.
It's not right here, but I can run the code for you.
Oh, you didn't really include the plot.
Yeah.
So okay, so yeah, here's the suggestion, right? Your project is more prone to be a research project, I would say. So in the research presentation, if you have done some benchmark, right, you better show it, right? If you just tell me, okay, the time is 11.8 times better, I won't know it. Where did you get this data? So of course the examiner or the supervisor will ask you about this question. So you better just show the benchmark, right? Or if you just source some papers and you don't really do the simulation, then you can just cite the papers correctly. Wow, but this is really marvelous. The only problem I noticed so far is really your functional block diagram. That's a problem, I'll say. It's not so good, but for others, I'll say it's quite good. It's quite good. I really like it. And another thing I want to draw your attention is basically some of the common problems I believe shared among your folks. Even past year, I also see this problem, which is the reflection, right? You mentioned about the limitation, but you showed me some advantages, but you didn't really redo the calculation, right? So as I mentioned earlier, right, in the the project briefing session, I told you guys that okay, when you are doing your component tries, you're actually using a bottom-up approach. Means that you make this you make this requirement, and following the requirement, I choose this, and choose that, and you integrate them together. Hope that will work. Right, and at the this kind of like a reflection session, what you need to do is redo the calculation, but following a top-down approach. Means that I have chosen this, I've chosen this, I've chosen this. Those are the components we have chosen, and I'll just following whatever logic I've defined, and then try to see if that matches our project specification. Right, this is the top-down approach, which is something you really want to add, but. I would say it's a common problem.
So actually we have like justified we use the 12-volt battery. This is the component we choose in our materials. And also motor thing. Essentially, we justify that it will work in our design, so we choose it and do the calculation.
You need to show me the justification. You can't just.
Yeah,
We
we show
show it in the calculation part.
because we calculate the total torque and the speed, which is satisfied for our designated speed, which is 0.2 meters, and our motor maximum speed is 0.641. So it is justified.
Okay. Better wrap it up at the final stage, so it's easier for me to see. But yeah, I would say it's a minor bug, but overall the flow is quite nice. And one more suggestion is, can you make the font a bit larger? It's very hard for me to see it. I know you want to cover a lot of stuff, but it's really a marvelous presentation. I really like the control logic, and yeah, I would say you should really run for a competition. Like, yeah, keep up the work. I can see a bright future unfolding in front of you guys. Yeah.
Also for the weight estimation was justified because the weight of this and the weight of the battery is 0.9, and we use estimation of 1 kg.
Okay, I see it. Okay, yeah, so maybe you want to organize your slide a bit better, and yeah, I really like your presentation, and I believe you guys have done a really good job. Okay, so yeah, we'll call it the end. Thank you.
Thank you.
Thank you.
Can you just send me the raw slide to me? Don't make any modifications, just email to me.
Okay.
Whatever you have, just email to me, okay? Thank you.